2.8, inverse and inverse trig functions. All right, so what we were doing yesterday is nothing involving calculus, really. We were just kind of reviewing an inverse. And two functions are inverses if they do what relative to each other? Undo each other's work, right. And the way that we can symbolize it algebraically is all the x and y information are going to what? Switch, flip, interchange, right? And that's what we saw over here. For the equations, you can interchange x and y and resolve for y, and then give it the f-inverse notation. And for a graph, you can actually do it with individual points. But then we reviewed the fact that if you have a graph, you can get the inverse graph by reflecting your original function across what magical mirror? Y equals x. And then the last thing we noticed was that the slopes appeared to be reciprocals of each other. Like in the equation on part B, we had a 5 and a 1/5. And if you were to analyze a couple of slopes over here, maybe the slope at -1, 0 and the slope at 0, -1, or maybe the slope right here at -3, 2 and 2, -3. Could it be that they're reciprocals of each other as well? Possibly. The corresponding points was an important thing. We defined that yesterday, right? Thank you. What are corresponding points when you're talking about a function and its inverse? Points that are flipped, right. So on the blue graph up here, the point -1, 0 is its x-intercept, and the corresponding point on its inverse, 0, -1, is its y-intercept. These 2 points correspond to each other. And if you want to look at them, these 2 points are always going to be reflected across the line y equals x. Those are the corresponding points. So we could say that with functions like this. We could say that if g of x is the inverse, and sometimes we define g of x to be the inverse simply because writing f inverse can be a little bit cumbersome and tedious, right? So if we define the inverse to be g, bless you, then if they are truly inverses, then if f of a equals b, that implies that g of b equals a. That make sense? So what that means then is on function f, there's a point called a comma b, and on the inverse function g, there's a corresponding point called b comma a. So what that means. Here's a very important property that inverses have that should help you identify them. A function g of x is said to be the inverse of function f of x if and only if this is true. And this is like an algebra 2 thing. If f of g of x equals g of f of x, and oh, by the way, both of them equal x, then you know that the two functions f and g are inverses of each other. So somewhere in algebra 2, you learned about composition. And you learned that in general, composition is or is not commutative. If you're buying that elephant blanket, remember from pre-cal, and the elephant blanket proprietor offers you a $5 discount and a 5% off, does it matter the order in which you take it if you're in the interest of saving money on your elephant blanket? Yeah, you should take which one first? The 5% off, and then take the $5 discount, right? It matters, because if you take the 5% off first, you're taking a discount of a larger amount, so there's more discount. That's applying two things in different orders, and it's in general not commutative. But when is it commutative? When is composition commutative? When the functions are inverses of each other. And not only is it commutative, they are always going to equal x, because notice the way that we read this. With your Jerry and Sally's rules, we start on the inside. So if I'm starting with x, let's say right here, and my function g takes me 2 steps to L's right, now I'm in front of Mr. Rapp. Now I apply the inverse. What's the inverse of 2 steps to the right? 2 steps to the left, and now I'm back in front of Mr. Clark, which is where I started, right? And if you look under my feet, there is an x. See, right here? See the x? So I'm right back where I started. Pretty sweet. Now what if I did it the other way? What if I stand here and I take 2 steps to L's left, my right, now in front of Vanessa, and what's the inverse of 2 steps to the left? 2 steps to the right. And now I'm back where I started at x. Are you impressed with my dance moves? Yeah. Okay. All right. So it makes perfect sense. Now, why do we need to review that? Am I going to have you like get 2 functions and prove that they're inverses by composing them? No, that's an algebra 2 thing. What you're going to have to do is identify that 2 functions are inverses when this relationship holds. Because what we're about to do is talk about how to find slopes of inverses. And you may just be throwing 2 functions that you don't recognize as inverses, But if you're told that this property exists between the two, you could be like, those are inverses, so they're going to have corresponding points. Yeah. Okay, so here's the graphical consequence of inverse functions. The graphs of function f of x and its inverse f inverse are reflections across the line y equals x. So what does this mean about the slopes of inverse functions? Here's in general a graph of f and its inverse f inverse in blue. There's 3 bullet points that I want to read to you, and they're all important. Yeah. The first bullet point says inverse functions at corresponding points have reciprocal slopes. You got that? Let's read the first bullet point one more time. Inverse functions at corresponding points have reciprocal slopes. Got it? Bullet point number 2. Inverse functions at corresponding points have reciprocal slopes. Let's read that one once more. Inverse functions at corresponding points have reciprocal slopes. Nice. And the third bullet point. Inverse functions at corresponding points have reciprocal slopes. Do they have opposite reciprocal slopes? Just reciprocal slopes. When do two things have opposite reciprocal slopes? When they are perpendicular to each other. But if they're inverses, they have just reciprocal slopes where? At corresponding points. Yeah, so you can shuffle the word order around, right? It's the beauty of sentence structure. At corresponding points, comma, inverse functions have what type of slopes? Reciprocal. We get reciprocal slopes on inverse functions where? At corresponding points. And for what type of functions do we have reciprocal slopes at corresponding points? Inverse functions. You think you're going to remember that? If not, go back and reread any one of those 3 bullet points. I would probably say the middle one. It's less exposed, so it's fresher. All right. We can state that mathematically like this. Let f and g be inverse functions of each other, such that this is true, right? If f and g are inverses, then we know f of g of x equals g of f of x, and they both equal x. Good to know. If f of a equals b, then we immediately know that g of b equals a. Yes, yes? What do we call a and b and A? Corresponding points. Yeah. Then g prime of b, come on in. Then g prime of b should be related to f prime of a how? Reciprocals. It's 1 over f prime of a. So notice that to find the slope of each graph, we use their inputs. A is the input for f, b is the output for f, but b is the input for g, and a is the output for g. So f prime of a and g prime of b are what's of each other? Reciprocals. Right. Okay, that's all this says. G prime of b is 1 over f prime of a. You can do it the other way around too, right? What is f prime of a equal to? 1 over g prime of b. Inverse functions at corresponding points have slopes that are what, Nick? Reciprocals. And we get reciprocal slopes for corresponding points at what type of functions? Inverses. Inverses and reciprocals aren't necessarily the same, are they? Okay. For instance, blah, blah, blah. Okay. Blah, 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 blah. Okay. Before trying it out, it's worth mentioning that inverse functions at corresponding points have reciprocal slopes. Is there a Quizlet for that? So you can just practice? Yeah. I should make one, right? Like 105 slides, and they're all the same. I inculcate this to you now, but later on in the year, guess what? I'm going to throw one of these problems that we're about to work right now, and you're going to be like, what? They have what? What? So, one more time, without the Quizlet, because we don't have the Quizlet yet. We get reciprocal slopes at corresponding points for what type of function? Inverses. Now, how in the world are we going to know that we have inverse functions when we're just given f and g? Right. We're either going to be told that that relation exists between the two, or the instructions will say f and g are inverses. That's nice. All right, example 2. If f of x equals x cubed, a 1-to-1 function, find the following. Okay, Let's just see what we're working with here. X cubed, that's a parent function. We know that it looks like the John Travolta disco graph, right? What type of tangent line does it have right there at 0? Horizontal. That's a singularity where we have a horizontal tangent, but it's monotonic increasing through that point, we say. Okay, we want to find f of 2, so this could be 2 right there. F of 2 is the slope of the tangent, or it's just the y value there, sorry. That's just going to be 2 cubed, which is 8. Right? That's easy. We should probably quiz now, huh? Quiz no. How about this? F of 2 equals 8. Good. So that's the ordered pair 2, comma 8. We're pretty good with establishing that at 2, that function equals 8. Yes? Okay, moving right along. What's f prime of x? Well, f prime of x, if f of x is x cubed, is 3x squared. Nice. That'll allow us to find the slope of the graph at any given point. I wonder what the slope is at 2. Well, that's what part C is asking us. F prime of 2 then is going to be 3 times 2 squared, which is 12. All right, let's come up here and make sense of what we just did. I just found the slope of this line here to be 12, and it happened at the point 2, comma 8. Nice. Uh-oh, someone must be here. Miss Corpy. Yes. Yes. Yes, she's welcome to come up. Yes. No problem. She's coming. She's on her way. All right, so here we go. She's not the photographer. So if she asks you a question, feel free to volunteer that. Okay. What is this? Is this f prime to the negative first? Is this to the f to the negative prime? F inverse. Okay, so how do we find f inverse? If f is equal to x cubed, and if f is just a fancy name for y, we interchange x and y, yes? And we resolve for y by taking the cube root of both sides? Do we need to do plus or minus when we take the cube root? No. Well, that makes sense, right? If the function cubes it, then the inverse function would uncube it, or cube root it. So f inverse of x is equal to the cube root of x, or x to the 1/3, if you prefer that. Either one, yeah? Okie dokie. F inverse prime. Holy moly. Okay, well, let's see. F inverse, remember, is x to the 1/3. So by the power rule, F inverse prime would be 1/3 x to the negative 2/3, which if I clean that up is 1/3 cube root of x squared. You could square it under or outside the radical. Now this says what's f inverse prime of 8. Notice how bulky that notation is getting, which is part of the reason why we usually define an inverse function to be just plain old g. So that's going to equal 1/3 cube root of 8 squared. And that's 1/3. The cube root of 8 is 2. 2 squared is 4. And then we get 1/12. Oh, my goodness. Oh, my goodness. Hello, Miss Block. Come on in. How are you doing?
Great.
We're in the middle of some awesome calculus right now. Yeah. Do you want to,
Well, so our photographer, Laura, was going to be coming by a little bit later. She couldn't come at this time.
Okay.
So she was going to be coming by to get pictures, but I'm going to be the reporter.
Okay.
So, what would be a good time?
We could, you want to ask me personal questions, or did you want to, observe, or did you want to ask them questions, or did you want to learn calculus?
Well, I don't know about calculus.
Yeah.
That's why I majored in journalism.
Oh, okay, cool, yeah.
But, yeah, I would love to kind of ask you some questions.
Okay.
And maybe if there's some students afterwards who,
Sure.
Yeah.
Yeah, let me finish this problem, and then I think it'll be a little disappointed if we stop for a little while, but right, I'll get over it. It is National Face Your Fears Day, and their biggest fear is running out of math, right? Okay, so, oh yeah, math. Silly. Yeah. 1/12. Okay, so let's see what we just found before we answer part G. We had the function f inverse of x, which was the cube root of x, and that's a parent function, right? What does the graph of x to the 1/3 of the cube root of x look like? Well, if you don't remember, you can always generate it by reflecting it across the line y equals x. We've seen that before. What's the value of the derivative right there at 0? No. Undefined. Undefined because it's some type of what? Vertical. The derivative has a vertical asymptote there because the derivative or the function has a vertical tangent line. So the slope is infinity there, right? But what we were doing is we found that the slope of that graph at 8, which is going to be, where am I? F inverse prime. We found the slope is 1/12. Notice my graph is not drawn to scale, 2, 8. So we're just going to have to say that this would be the corresponding point. And I know that because I reflected across the line y equals x. So anyway, let's draw that. What do we just find the slope of that to be? Sometimes when you don't draw things to scale, it kind of backfires. But you know what's good? Because graphs can be misleading, right? And calculators will lie to you sometimes. But guess what's always true? The math, right? The math. When you don't make careless mistakes, it's always true. So we kind of went the proper way to find the slope of f inverse at 8 to be 1/12. This is coming in through the celebrity entrance, right? What's the reciprocal of 1 over f prime of 2? What do we find f prime of 2 to be? 12, right? What's the reciprocal of 12? Don't think too hard. 1/12. And is that the same thing we got here? Yes. And so here's what actually happened. And of course, ignore the scale because that really messes it up. We had the function f of 2 equals 8, right? And that means that on function f, there's a point called 2, 8. G ended up being f inverse. Let's just call it f inverse. We said of 8, it equals 2. That's what we found. So on f inverse, there was a what kind of point? Corresponding point called 8, 2. And what do we know about the slope of f inverse at 8 compared to the slope of f at 2? They are what's of each other? Reciprocals. Yes. So in the future, here's what we could do. If you're trying to find f inverse prime of 8, and you know that 8 is the output for f, then it's going to be, or you know it's the input for f inverse, you know it's going to be the output for f. All you have to do is find the slope of f at its input too, which is a lot easier to find, right? Because you don't have to actually switch x and y and find the inverse and then take the derivative. You just find the slope of f at its input and then do what with your answer? Flip it. Yeah. Find the reciprocal of it. So we were able to do it both ways here. We can actually find the inverse equation and take its derivative. Do you think we're always going to be able to find the equation of the inverse? No. And you know what? We don't really need it now because we have this nice sneaky way to get the answer. So let's answer these two questions, or these three right here on example 3, because I want to kind of tie in that idea. If f of x equals x to the 5th plus 2x minus 1, it's a 5th degree polynomial, right? See that? Where is it differentiable? Everywhere. Good. So where is it continuous? Everywhere. It says to use f prime in the continuity of the function to show that, first of all, f is 1-to-1. That's kind of a hint. How are we going to use f prime to show that it's 1-to-1? Well, I guess first I need what? F prime. Let's find it. F prime of x is 5x to the 4th plus 2. Okay. So that itself is also a polynomial. So where is that derivative function continuous? Everywhere, right? If I plug in any value of x, what type of number am I going to get out? I should get out a positive number, right? If I plug in a negative, it's going to be to the 4th power, so it's going to be positive. Times 5 is positive, plus 2 is positive. The lowest this is going to be is when it's 0. 0 to the 4th times 5 is 0 plus 2. So this thing is going to be 2 or greater, yes? So I know that this is going to be strictly greater than 0 for which values of x? For all x. And remember, you can use that that inverted A, right? And just say for all x in the set of real numbers. Now, what does it say about the function f if its derivative is always positive? It's upbeat, it's optimistic, it's cheerful, even on a Monday, right? Good. So f of x is monotonically, I like that, making it into an adverb. Or you could say strictly. That's another word that is the same thing. Is strictly increasing. Now, is every function that's strictly increasing going to be one-to-one over its domain? No. Can you give me an example of a function that's strictly increasing over its domain but is not monotonic or not one-to-one? A function that's increasing everywhere over its domain but it's not one-to-one. The absolute value of x? Well, the absolute value of x is decreasing and then increasing. A piecewise tangent is the example that I'm thinking of. Because tangent, remember, has vertical asymptotes how often? Every pi halves. So you get pi halves, every odd pi halves, right? 3 pi halves. And what's it doing in between them? It's increasing. So over its domain, it's monotonically increasing. But is it one-to-one? No, because to be one-to-one, it has to pass what line test? The horizontal line test. Fail, 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 right? It fails miserably. Or would that be failing greatly? Depends what you're going for, right? If you don't want to fail, then I guess you're failing and you're miserable. But if you plan to fail and you fail miserably, that's actually success. So I don't know. But is this going to be the case with us right here? What's different about the graph of tangent than our graph? Our graph is what? It's one-to-one. Why? Because not only is it monotonically increasing over its domain, but it's also what? Continuous. Yes. Continuous. That's a huge part. So f of x is monotonically increasing and continuous. And continuous, comma. So what? F of x is one-to-one. It's the Mickey and Minnie of functions, right? 1x for 1y, 1y for 1x. So what does that mean now that it's one-to-one? Does it have an inverse? Yes. If it's one-to-one, remember, there's only one way to code a message and only one way to decode it. We call that invertible, if you want to write that down. A function that's one-to-one, we say, is invertible, which means it has an inverse. That's what it means. It has an inverse. So in the early days of like encryption, you know, this was long before the internet. These one-to-one functions that were invertible made good ciphers. You could code a message, and there's a lot of one-to-one polynomial functions, and someone on the other end could decode your message if they knew the polynomial that you used to translate your letters from the alphabet. So it's like an early cipher. These are one-to-one. But for us now that I know that it's one-to-one, I can answer the following questions. What is f of 1? Well, we don't need to know it's invertible for that, but what is f of 1? How do you find that? Plug it in. What do you get? 2. I get 2 also. All right. So if I know that f has an inverse now because it's one-to-one, and I know that there's a point on the function f called 1, 2, then I know that there's a corresponding point on its inverse, which I'll call f inverse, to be what? 2, 1. And here's what I know before I even look at what the next question is asking. I know that the slope of my graph of f at 1 and the slope of the graph of f inverse at 2 are related how? Reciprocals of each other. Yeah, okay. So here now it says find f inverse prime of 2. Find f inverse prime of 2. Well, you could do it the way we did it before, right? I could come back up here, and I can interchange my x and y and resolve for y. Can we do that? If I want to. Solving this when I change the variables for y is tantamount to solving this for x. Are we going to be able to solve this for x? No. It's going to be very, very difficult. Well, guess what? We have a sneaky way to get the answer now, don't we? Sneaky way. right? You want f inverse prime of 2? No problem. I know it's going to be the reciprocal, right? 1 over f prime of what? 1. 2 is the input on f inverse. 1 is the input on f. So now, how hard is it to find f prime of 1 if I have f? Rather easy, right? Easy cheesy, lemon squeezy, sneezy. Let's try it. We got f prime of x, which is what? Hey, we already found it. Why find it again? Now we need what? F prime of what? 1. Let's find f prime of 1. We'll sneak it in right here. F prime of 1 is, don't mess up, there's a lot at stake here, 7. Nice. And now the fun part. You get to flip 7. Flip 7. 7. No, I think it would flip this way. No? Let's see. Flip that. Yeah, it would be like that. That's right. You got to be careful when you say flip, right? People can get the wrong impression. We reciprocate it, right? And we get 1/7. There you go. That was really the only way to do that problem without a calculator, yes? Because there was no way to find the inverse equation of that. But yet, we were still able to talk about its slope of this graph whose equation we didn't even know at a certain point. That's pretty cool, right? All right, so just to end today's lesson, because we're not quite due with the whole thing, we'll finish tomorrow. One more time. Inverse functions at what type of points? Corresponding points have what type of slopes? Reciprocal slopes. Okay, very good. We be done.